Welcome back. For 5 episodes, we have built the machinery of second-order linear equations with constant coefficients. Today, we cash it in on the single most important application in all of applied mathematics, the vibrating mechanical system. Picture a block on a table tied to a wall by a spring with a shock absorber attached. Pull it and let go. What happens? Newton's second law turns that picture into one equation, m times x double prime plus c times x prime plus k times x equals 0. We will solve it completely, first with no damping, where the mass oscillates forever at a fixed natural frequency, then with damping, where the motion splits into 3 distinct personalities depending on a single number, and finally the payoff. The very same equation runs an electrical circuit. Master one differential equation, and you have mastered 2 entire branches of engineering at once. Let's build the model honestly. Let x of t be the displacement of the mass from its rest position, positive in one direction. 3 forces act on it. The spring pulls it back toward rest. By Hooke's law, that restoring force is minus k times x, where k, the spring constant, is positive and measures stiffness. The farther you stretch, the harder the spring pulls back. Second, the damper, or dashpot. Think of a piston moving through oil. It resists motion in proportion to velocity, so that force is minus c times x prime, where c, the damping constant, is greater than or equal to 0. Now apply Newton's second law, mass times acceleration equals the sum of the forces. Mass times x double prime equals minus kx minus cx prime. Move everything to one side, and we get mx double prime plus cx prime plus kx equals 0. That is a homogeneous, second-order, linear, constant coefficient equation, exactly the kind we already know how to solve. The characteristic equation is mr squared plus cr plus k equals 0, and its roots, through the quadratic formula, control everything that follows. Start with the simplest case, no damping at all, c equals 0. The equation becomes mx double prime plus kx equals 0. The characteristic equation, mr squared plus k equals 0, has no real roots. Instead, we get a pair of pure imaginary roots, plus and minus I times omega naught, where omega naught is the square root of k over m. We call omega naught the natural frequency, and it is the single most important number in the whole subject. Complex roots mean the solution is a combination of cosine and sine at that frequency, x of t equals c1 cosine omega naught t plus c2 sine omega naught t. Using the amplitude phase form, that is a single cosine wave, capital A cosine of omega naught t minus phi. The amplitude A is the square root of c1 squared plus c2 squared, and phi is a phase shift set by where the mass starts. This is simple harmonic motion, the purest oscillation in nature. It repeats with period 2 pi over omega naught, and crucially, it never dies down, because with no damping, no energy is ever lost. A frictionless spring rings forever. Now turn the damper on with c greater than 0. The roots of the characteristic equation are minus c, plus or minus the square root of c squared minus 4 mi c all over 2m. Everything hinges on the quantity under that square root. The discriminant, c squared minus 4 mi c. It can be negative, 0, or positive, and each case is a completely different kind of motion. If the discriminant is negative, which happens when damping is small, the roots are complex and we get underdamping, a decaying oscillation. If the discriminant is exactly 0, the roots are a single repeated real number and we get critical damping. And if the discriminant is positive, with large damping, we get 2 real negative roots and overdamping. The dividing line sits at the critical damping value, C critical equals 2 times the square root of mk, which also equals 2m omega naught. Dividing the actual damping by this critical value gives the damping ratio, zeta, a single dimensionless number that tells you instantly which of the 3 worlds you are in. Take the underdamped case first, where damping is light and the discriminant is negative. The roots are complex, a real part of minus c over 2m, plus or minus I times a new frequency omega 1. That omega 1, the square root of 4 milli-c squared, all over 2m, is called the quasi-frequency, and it equals omega naught times the square root of 1 minus zeta squared, always a little slower than the undamped natural frequency. The solution is a cosine wave multiplied by a decaying exponential. X of t equals a times e to the minus c over 2m times t, times cosine of omega 1 t minus phi. So the mass still oscillates, but each swing is smaller than the last, because the whole wave is trapped inside a shrinking envelope of plus or minus ae to the minus c over 2 min t. This is the sound of a plucked guitar string or a struck bell. It rings at a definite pitch, and that ringing fades smoothly to silence. Light damping does not stop the oscillation, it slowly starves it. Now the 2 heavily damped cases. Overdamped with a positive discriminant gives 2 distinct real roots, both negative. The solution is a sum of 2 decaying exponentials, c1e to the r1t plus c2e to the r2t, and it sinks back to rest without ever oscillating. It can cross 0 at most once. Think of a screen door with a strong closer, easing shut slowly. Critically damped with discriminant exactly 0 gives a repeated root minus c over 2m. As we learned for repeated roots, the solution is c1 plus c2t, all times e to the minus c over 2mt. Here is the beautiful fact: critical damping is the fastest possible return to rest with no overshoot. Any less damping and the system overshoots and wobbles anymore, and it crawls back lazily. Exactly at critical, it returns as quickly as physics allows and stops clean. That is why door closers, car suspensions, and the needles on analog meters are all tuned right at or just past critical damping. Let's see all three regimes on a single graph of displacement against time, every curve starting from the same pulled back position. The blue curve is underdamped. It oscillates, swinging above and below the rest line, but each swing is smaller than the last because it is trapped inside the decaying envelope. This is the only curve that actually vibrates. The gold curve is critically damped. It slides back to rest smoothly and quickly, never crossing below 0, never overshooting, the fastest clean return. The red curve is overdamped. It also returns without oscillating, but notice it is slower than the gold critical curve, lagging above it the whole way down because too much damping makes the system sluggish. The key visual lesson is that more damping is not always better. Past the critical setting, adding damping actually slows the return. Critical damping, the gold curve, is the sweet spot that engineers chase. Let's put numbers to it. Take a 2 kilogram mass on a spring with stiffness 50 newtons per meter and no damping. We pull it to 10 centimeters, that's 0.1 meters, and release it from rest. First, the natural frequency, omega naught, equals the square root of k over m, the square root of 50 over 2, which is the square root of 25, which is 5 radians per second. The general solution is c1 cosine 5t plus c2 sine 5t. Now apply the initial conditions. At time 0, x equals c1, and that must equal 0.1, so c1 is 0.1. The initial velocity is the derivative at 0, which is 5 times c2, and that must be 0 since we released from rest, so c2 is 0. The motion is therefore x of t equals 0.1 cosine of 5t meters. The mass swings between plus and minus 10 centimeters forever, with a period of 2 pi over 5, about 1.26 seconds per cycle. Clean, simple harmonic motion. Same mass and spring, now with damping. First find the critical damping. C critical equals 2 times the square root of mk, the square root of 2 times 50, which is the square root of 100, times 2, that's 20 newton seconds per meter. Any damping below 20 is underdamped, anything above is overdamped. Test C equals 4. 4 is well below 20, so it is underdamped. The roots work out to minus 1 plus or minus I times omega 1, where omega 1 is the square root of 25 minus 1, about 4.9, barely slower than the undamped frequency of 5 since the damping is light. Now test C equals 30. 30 is above 20, so it is overdamped. Solving 2r squared plus 30r plus 50 equals 0 gives two real negative roots, about minus 1.9 and minus 13, two decaying exponentials, no oscillation. And right at C equals 20, we would get the repeated root minus 5, the critically damped boundary between the two behaviors. Let's finish the underdamped case completely with the same release from 10 centimeters at rest. With C equals 4, the roots are minus 1 plus or minus I times omega 1, where omega 1 is the square root of 24, which is 2 root 6, about 4.9. The solution is e to the minus t times the quantity c1 cosine omega 1t plus c2 sine omega 1t. Apply the initial conditions. At time 0, x equals c1, so c1 is 0.1. For the velocity, differentiate using the product rule. At time 0, the derivative is minus c1 plus omega 1 c2, and that must equal 0, so c2 equals 0.1 over omega 1, about 0.02. So the full motion is e to the minus t, times 0.1 cosine omega 1t plus 0.02 sine omega 1t. The mass oscillates at roughly 4.9 radians per second, but its amplitude shrinks by a factor of e to the minus 1, about 37%, every single second. After a few seconds, it has effectively stopped. Here is the payoff that makes this episode count twice. Take an electrical circuit with 3 components in series, an inductor, a resistor, and a capacitor, and let Q of t be the charge stored on the capacitor. Kirchhoff's voltage law gives L times Q double prime, plus R times Q prime, plus 1 over C times Q equals 0. Look at that equation. It is identical in form to mx double prime plus cx prime plus kx equals 0. The mathematics does not care whether the symbols mean a mechanical system or an electrical one. Inductance L plays the role of mass. It resists changes in current the way mass resists changes in velocity. Resistance R plays the role of damping. It dissipates energy as heat the way friction does. And 1 over the capacitance plays the role of spring stiffness. The natural frequency is 1 over the square root of LC, so everything we just learned, natural frequency, underdamped ringing, critical damping, applies word for word to circuits. 2 subjects, 1 equation. A little history. In 1678, Robert Hooke published his spring law as a Latin anagram, later revealed as ut tensio sic vis, as the extension, so the force. That is exactly R minus kx, force proportional to stretch. Combine Hooke's law with Newton's second law, force equals mass times acceleration, and you immediately get mx double prime plus kx equals 0, the harmonic oscillator. Over the 18th and 19th centuries, Euler, Lagrange, and many others discovered that this same equation governs pendulums, vibrating strings, sound waves, and the bending of elastic beams. Then the electrical age arrived, and physicists like Lord Kelvin recognized that a circuit with an inductor, a resistor, and a capacitor obeys the identical equation, the electromechanical analogy that lets engineers simulate mechanical systems with circuits and vice versa. One little differential equation, 3 centuries of physics, and essentially every branch of science that deals with anything that vibrates. Let's recap. From Newton's second law and Hooke's law, we built the spring mass damper equation, mx double prime plus cx prime plus kx equals 0. With no damping, we get simple harmonic motion, a cosine wave at the natural frequency omega naught, the square root of k over m, that oscillates forever. Turn damping on, and the discriminant c squared minus 4 meters k decides the behavior, with the boundary at the critical damping value 2 times the square root of mk. Underdamped, with small damping, gives a decaying oscillation inside an exponential envelope. Critically damped gives the fastest possible return to rest with no overshoot. Overdamped, with large damping, gives a sluggish return built from 2 decaying exponentials and no oscillation at all. And finally, the same equation runs an electrical RLC circuit, with inductance playing the role of mass, resistance the role of damping, and the reciprocal of capacitance the role of stiffness. Next time, we push the spring from outside with a rhythmic force, and discover resonance, where pushing at just the right frequency can tear a system apart. Today, we solved the spring mass damper. Newton's second law gives mx double prime plus cx prime plus kx equals 0, where m is the mass, c is the damping constant, and k is the spring stiffness. With no damping, the solution is simple harmonic motion. X of t is a cosine wave at the natural frequency omega naught, which equals the square root of k over m. The mass oscillates forever with constant amplitude. Turn on damping, and the characteristic equation, mr squared plus cr plus k equals 0, decides everything through its discriminant, c squared minus 4 miller k. When that quantity is negative, we get underdamping, a decaying oscillation that rings down inside an envelope of e to the minus c over 2m times t. When it is positive, we get overdamping, 2 real negative roots, and a slow crawl back to rest with no oscillation. When it is exactly 0, we get critical damping, a repeated root, and the fastest possible return without overshoot. Finally, the same equation runs an electrical circuit. An inductor, a resistor, and a capacitor in series obey LQ double prime plus RQ prime plus 1 over C times Q equals 0, identical in form, so inductance plays the role of mass, resistance the role of damping, and the reciprocal of capacitance, the role of stiffness. Next time, we push the system from the outside and meet resonance. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.